wicked! Fireworks!
Hi everyone, welcome to another video in my vanilla JavaScript and HTML5 canvas animation series where we create all different kinds of interactive animated effects from scratch with no libraries, using just pure vanilla JavaScript. Before we start, don't forget to click the like button if you want more videos like this one, subscribe and click the bell icon to get notified when I release a new tutorial. Today, we will be building animation you can see in the background right now. We will turn image into particles and make them interact with the mouse. If you want to see more animated effects, check out my channel. This video is part of a series, but also it is completely independent. I will code everything from scratch, but I might not explain every single detail in depth if I explained it already in previous episodes. This is advanced JavaScript, but I will do my best to make sure even beginners can follow and create this cool effect for your personal website or just to show off on your GitHub profile. There are many ways to structure code like this. I'm making sure all the videos in the series are structured in the same way so you can focus only on the new techniques. This video will as usual have JavaScript particle class to create each particle as an object. Each particle will have a draw and update methods and init and animate functions to randomize values and create animation. New things we will learn today is first of all how to work with images on a HTML canvas, mainly drawImage and getImageData methods, which will give us information about individual pixels. These methods are available on Canvas object. I will show you how to use plain vanilla JavaScript to transform the output into X and Y coordinates, and another small JavaScript algorithm will extract correct color values for our particles. Second new thing we haven't done in this series yet, instead of just simply pushing particles with mouse, like you can see in this example of my first few attempts, we will give particles some elasticity, friction, to make the movement more natural. You can see in the old examples, particles move in linear speeds. They are either not moving or moving the same speed all the time. I want their movement speed to be more dynamic, depending on the current distance of that particle from the mouse. In this example, you can see particles move fast at first, but slow down as they reach the radius of circle I defined around the mouse. As usual, if you stay until the end of the video, I will show you a few ways to tweak this code to achieve different results. For example, how to get particles attracted to the mouse instead of being repelled. Hope you like this video. I spent a lot of time trying to figure this out and make the code as clean and as simple as possible so everyone can follow. Also, who can name all the pop culture references in this intro? Let's start. We will work with three files: index.html, style.css, and script.js. In index.html, we just link our style sheet and script.js file and create HTML5 canvas element with an ID of canvas 1. In the style CSS, we give our canvas position absolute, top 0, left 0, width 100%, and height 100%. Everything else will be done with JavaScript in the script.js file. Let's start by declaring basic canvas variables. I grab the canvas with getElementById and save it in a constant variable I called canvas. Then we call getContext2D on our canvas element and save it as CTX, shortcut for context. We set canvas width to window inner width and canvas height to window inner height. I will also declare a variable for particle array, which we will later use to store individual particles as objects that will contain position and color values for our particles. As you saw in the examples, we turn our image into particles and make the particles interact with the mouse. To do that, we need to know the current position of the mouse at any time. I will create custom mouse object and give it X and Y properties and set them to null for now. We will also need radius property, which will define the size of a circle around the mouse within which the particles react to the mouse. Now I can create event listener for mouse move event. Every time mouse move event is triggered, callback function will run. This function by default has access to the event object. I will set mouse x to event.x and mouse y to event.y. I have also added client left value to the mouse x position and client top value for mouse y position. You can ignore these values as this is not necessary with the current canvas setup. I will create custom drawImage function. You can call it whatever you want. Following code needs to be inside of a function so I can later attach it to a load event. The reason is that all the code inside this function needs to be run only after the image has been fully loaded, which will only take a few milliseconds, but JavaScript is fast and if we don't wait those few milliseconds we will get an error. I will declare a variable image width and set it to png.width, and image height will be png.height. PNG will be declared at the end of the file since it's a long Base64 code. I will show you how to easily convert any PNG image into Base64 code in a minute. I will also provide you with images I created for this project along with their Base64 code in the video description below, in case you don't feel like creating your own. I declare a constant variable called data and I set it to ctx.getImageData. This is a method on Canvas 2D API that returns ImageData object representing underlying pixel data for a selected position on the canvas. I will specify the canvas area by giving it start coordinates of 0, 0 and width and height of the area we want to extract pixel values from. I'm basically asking this method to scan a specified area of the canvas for pixel information, and I'm saving that information in a variable I call data. Remember, we will be calling this entire function a bit later. We have to wait for the image to be fully drawn first. Now we have the image data information and we can clear the canvas and delete the actual image. We don't need it anymore. I call ctx.clearRect 0, 0 canvas width, canvas height to clear everything. I create custom JavaScript class I call particle that will be used as a blueprint to create each individual particle as an object. These particles will make up our pixelated interactive image. Every class needs a special mandatory constructor method for creating and initializing an object created within a class. Here we define properties that will be shared between all particles. Some will be passed as arguments from our ImageData object, in this case x, y, color and size. We will pass these values here a bit later using a function I call init. Other properties will be calculated based on values passed as arguments to our particle class constructor. This.x will be x value coming from ImageData object, but since the image is smaller than our canvas, I want to center it in the middle. I do that by adding canvas width divided by 2 minus png.width, which is width of our image, times 2. I do the same for y. This y equals y value that is coming from ImageData object plus canvas height divided by 2 minus png height times 2. I am referencing some values I haven't extracted yet and variables I haven't declared yet. It will all make sense in a minute, just follow along with me. This.color is equal to color, which again will be passed as an argument and extracted from data object a bit later. This.size will be 2 for now. This.baseX and this.basey will be identical to this.x and this.y. We need to store these values in separate variables because we want particles to remember their initial position in the image before we move them around as they interact with the mouse. This.density will be a random number between 2 and 12, which will define how fast the particles move away from the mouse. Some will be heavy and move slower, some will be light and fly away from the mouse fast. I will also declare draw method in our particle class. This method will be called for each particle for every frame of our animation after x and y position has been calculated. We will use canvas arc method to draw a circle around particle's current coordinates. Update method will also be called for every frame of our animation, and this is where we calculate particles' movement and mouse interactions. First, I set fill style to this.color. I need to know if the particles are close enough to the mouse to start interacting. This is called collision detection. We will use simple 2D circle collision detection algorithm. Since our mouse has a circular area around it defined in mouse.radius, and each particle is a circle drawn with canvas arc method, this algorithm will just compare the distance of their two center points. If the distance is less than 2 radii of these circles added together, we know that mouse and particle are colliding. So the common formula goes like this. I declare dx variable, this stands for delta x. This will be equal to mouse.x minus this.x, so the current position of the mouse on the x-axis minus the current position of the particle on the x-axis. dy will be mouse.y minus this.y. From that, we can calculate distance doing math square root dx times dx plus dy times dy. I create variable called force direction x, which is equal to dx divided by distance. Force direction y will be dy divided by distance. Now we know how fast the particle is being pushed along the x-axis and how fast it is being pushed along the y-axis. By combining these two values, we have a simple vector, direction of movement. I want force to scale between 0 and 1 depending on the distance. I will convert values between 0 and max distance into a range between 1 and 0. Close particles will have force value near 1. Faraway particles will have force close to 0. I achieved that with this calculation. Parentheses max distance minus distance, close parentheses, divided by max distance. Also, we don't want force to be negative numbers, so if force is less than 0, force is equal to 0. I include force and particles density in the final calculation. Direction x is equal to force direction x times force times this dot density times 0.6 to slow it down a bit. Direction y is force direction y times force times this dot density times 0.6. So collision detection, if distance is less than mouse dot radius plus this dot size added together, this dot x minus equals direction x, this dot y minus equals direction y. Direction x and direction y combined give us a movement vector, which is a fancy way of saying speed and direction of movement for each particle. Else, which will run every time particle and mouse are not colliding, we do additional checks. If this dot x is not equal to base x, which is where we store particle's memory of its original location, we calculate dx. This will be the difference between this dot x and base x. In other words, between particle's current position and particle's initial position in the image. This dot x minus equals dx divided by 20. I divided by 20 to slow down the speed in which particles travel back to the original position. We do the same for this dot y. Once all these positioning calculations taken place, we can finally call this dot draw, which will take current x and y position and draw our particle there. JavaScript will run all these calculations for each particle for every frame of our animation. Impressive, isn't it? That's why I use smaller image. I can imagine in future, when computers get more powerful, we will be able to do this effect for the entire website. Now I step out of particle class, but I stay inside our custom drawImage function. I will declare another custom function, I call it init. Its job is to extract position and color information from ImageData object and store it in particle array. First, I set particle array to an empty array in case it's not empty at the moment. I create nested loops, which means loop inside of another loop. I'm using slightly unusual syntax here, but bear with me. I'm just basically declaring two variables inside of a loop instead of just one. So, let y equals 0, y2 equals data height. As long as y is less than y2, y++. We enter the inner loop. Let x equal 0, x2 equals data width. As long as x is less than x2, we increment the x++. y2 and x2 could have been declared outside of the loop, but this syntax works, so I'm doing it. Quick explanation of nested loops. For each y, which is a column, we run through all x positions over and over. X represents rows. I'm basically scanning the image column by column and extracting pixel information. The code goes y0x1, y0x2, y0x3, y0x4 until we reach the bottom of the image and last x. Then we exit the inner loop, y++, will run and we enter the inner loop again and we move on to the second column, y1x1, y1x2, y1x3, y1x4 and so on. Hope I'm explaining this clearly. We are keeping it simple since I'm using PNG image 100 x 100 pixels, so for each pixel in our 100 x 100 grid, I set position x to be equal to x and position y to be equal to y. I also want to calculate color for each particle. Remember that our data variable holds output of getImageData canvas method. Pixel information is held in this weird thing called uint8 clamped array. I don't even know how to read that. Great job whoever came up with that name. This array holds a series of numbers between 0 and 255. As you know, colors can be defined in RGBA, where each number between 0 and 255 represents an amount of red, green, blue and alpha. That combined together create the final color. Yes, any color can be made by combining just red, green and blue. Isn't physics amazing? This array holds 4 values for each pixel. 1 for red, 1 for green, 1 for blue and 1 for alpha. These values are always between 0 and 255. This means every 4 positions in the array combined together represent color for 1 pixel. We will have to build a small algorithm to account for that and extract correct colors. In this case, I'm only interested in the first 3 values. I will concatenate RGB plus the value of red, which will be data.data y times 4 times data width plus x times 4. Green channel will be y times 4 times data width plus x plus 4 plus 1. And blue channel will be data.data y times 4 times data width plus x plus 4 plus 2. I will save the final RGB value as a variable I call color. Now I call push method on our particle array and pass it new instance of our particle class by using the new keyword. Our particle class constructor expects argument values for x, y, color and size. I will omit the size for now and pass it just the first 3 values, x, y and color. For performance reasons we are using just small 100 x 100 pixels PNG image, but I want that image to appear much larger on our canvas, so I multiply x and y by 4, so we get 400 x 400 image. I step out of the init function but still stay within our custom drawImage function and I create function I call animate. Here I call request animation frame API and pass it its own name as an argument. This will cause it to call itself recursively over and over and create our animation loop. Since I want our particles to leave trails, instead of clearing the canvas every step of the animation, I will set fill style to black with 0.05 opacity. And I will be drawing this black semi-transparent rectangle over our entire canvas over and over. This way, we can see previous positions of our particles slowly disappearing. This is a very simple way to get particle trails effect, but it is not suitable for every animation. In a future video, I will show you a better way to do this. Now I create a for loop to iterate over our particle array, which is full of particle objects. Each of these objects was created with particle class, so they all have access to custom update method. For each frame of our animation, I run through the entire array and call update for every single particle. That's a lot of calculation JavaScript has to do if you're running 60 frames per second. I've only declared init and animate. I also have to call it here. We have a small issue. When the user resizes window, canvas stretches. I will create event listener for resize event, and every time the event gets triggered, callback function will run. That will set canvas width to inner width and canvas height to inner height. An init function will refill particle array with x and y coordinates, centering the image in the middle of our new canvas dimensions. Now we can step out of our custom drawImage function. I create a constant variable I call PNG and set it to new image. This is a constructor which will create a new instance of HTML image element. It has the same function as calling document.createElement.img. We give our image element src attribute and set it equal to so-called Base64 PNG code. To get this code, you can Google PNG to Base64 converter or go to website onlinepng-convert-png-2-base64. It will convert any PNG to Base64 for you. Just make sure it's 100 x 100 pixels and transparent background. I will leave a link in the video description where you can download a bunch of nice images I created for purposes of this tutorial. They are already good size and ready to use. I will also include text file with Base64 code for all these images. We just paste that code into our HTML markup. We will need to create event listener for load event. This code will run only after our image has been fully loaded. I will call drawImage canvas method on our CTX variable. This method is part of Canvas 2D API and its job is to draw image we pass to it in the first argument, to x and y coordinates we pass to it in the second and third argument. I'm really sorry I named my custom drawImage function the same name as predefined canvas method. That was not the best decision on my part. Once we have drawn the image, we call our custom drawImage function to run all the code we have just written. Just to clarify, this method is part of Canvas API used to draw image on canvas. This is a custom method I created in this tutorial and can be named whatever you want. Congratulations on following all the way through. Don't feel bad if you don't understand some parts of the code yet. I went through it over and over so many times before I finally clicked on some of these calculations. Every time you do a tutorial like this, your brain becomes a bit more adjusted to this kind of thinking and you are becoming a better developer. I have some simpler and some more advanced vanilla JavaScript tutorials coming to the channel soon. In each one we will create awesome animations. Also, if you haven't seen the previous episodes in the series, you should see the link on the screen right now. That's all for today. Thank you very much for watching. Don't forget to click the like button, subscribe to the channel, and I'll see you next time.